This is example under gradient, divergence, and curl. So let's first take this example under gradient. So given f a, 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 scalar field which is equal to x squared y times z cubed, determine the gradient of that f at point 1, 1, 2. So this is in rectangular coordinate system, so solution. So we don't need to convert them first into rectangular. We can use our del operator in rectangular coordinates. So we need to determine the gradient. So the formula or the equation for the gradient, that's just the nabla or del operator times f, that vector f. So this will be equal to the partial derivative of f with respect to x in the x direction plus partial derivative of f with respect to y in the y direction plus partial derivative of f with respect to z in the z direction. So we have f equals x squared plus y times z cubed. So this will be the partial derivative of x squared y times z cubed in x direction plus the partial derivative with respect to y of x squared y z cubed. This is our f. Then for the z component with respect to z of x squared y z cubed in the z component. So how do we take the partial derivative? For the first term, we are taking the partial derivative with respect to x. So we treat other variables constant. So here, we treat y and z cube as constant. So we can just take out that constant z cube, then take the derivative of x squared with respect to x. And that derivative is just equal to 2 times x. This is in the x direction. And for the second term, again, we take the derivative with respect to y. So the other variables, I can just take it out side the derivative x squared and z cubed. Then you multiply it with the derivative of y with respect to y. That's just equal to 1 in the y direction. Then this is with respect to z. So we take out x squared times y times the derivative of z cubed with respect to z. That is just 3z squared in the z direction. So therefore, the gradient field will be equal to 2x y z cubed in the x. Then we have x squared z cubed in the y direction and 3x squared y z squared in the z direction. So this is delta f in xyz. Now we want to determine the actual gradient, the magnitude of that gradient at 0.112, or the vector of the vector gradient at 1, 1, 2. So 1, 1, 2 means this is uh, x equals 1, y equals 1, and z equals 2. So we just need to substitute this to determine the actual vector of the gradient. So this will be equal to, so vector at 1, 1, 2 now will be equal to 2 times x is 1, y is 1, z is 2. So 2 cubed in the x direction plus 1 again squared times z is 2 cubed in the y direction plus 3, 1 squared times 1 times 2 squared in the z direction. So the vector now, delta f, will be equal to 2 times 2 times 2, 4 times 2, 8 times 2, 16ax plus 2 times 2, 4 times 2, 8 times 1, 8ay, then plus 2 times 2, 4 times 1, 1 times 3, 12, so 12az. So this is now the vector at 0.112. So this is the actual vector at 0.112, the gradient vector at 0.112. So you can also determine the magnitude if you want. The magnitude of that vector will be just equal to the square root of 16 squared plus 8 squared plus 12 squared. And this is around 21.54. So this is an example under gradient. Next under divergence. So let's take this example here under divergence. So given a vector field E here, determine the divergence of this vector at point 1, 1, 2. So again, if we remember, the divergence means this is the dot product between the del operator and that vector E. And this is just equal to the partial derivative of the x component with respect to x. So we already derived this. Partial derivative of E with respect to x. The x component only. It's not the whole E. Unlike the here, the gradient that we take the partial derivative of the whole scalar field. Here we only need to take the partial derivative of the x component with respect to x, then take the partial derivative of the y component with respect to y, and also partial derivative of the z component with respect to z. Z. And let's do this. What is ex? The x component is just xz. So this will be partial derivative with respect to x of x times z. Plus for ey, we can take out that negative here. So minus partial derivative with respect to y of y squared. That's the component here of e at y component. For the z component, this is the z component. This is the x. So this is ex, this is ey, and this is ez. So partial derivative with respect to x of ez, which is 2x squared times y. And let's do the partial derivative. Here, z is constant. Partial derivative of x is 1, so the answer is z. Here we have y squared. So it's just y squared. So just 2 times y. Then plus, for this one, this should be with respect to z. And I don't see z in this component. So this means this whole thing is just a constant. So the derivative of a constant is just equal to 0. So we have z minus 2y. Now we want to evaluate this at 1, 1, 2. So again, meaning x equals 1, y equals 1, and z equals 2. So the divergence now of vector E at 1, 1, 2 will be, this will be equal to 2 minus 2 times 1. And that will be equal to 0. So the divergence is equal to 0. So this means divergence, the strength of the field entering that point is the same as the strength of the field leaving that circle at 1, 1, 2. Next, for the curl, this one, given a vector field equal to this one, determine the curl of the curl of f. So this is somewhat more difficult compared to the previous two examples. And at the same time, this is a cross product because we are determining the curl. Then we want to determine the curl twice. Determine the curl of f, and determine that curl again. So solution. So first, let us determine the curl of f. So this is just del cross f. And using the matrix method, I don't remember the formula, but you can still use the formula if you want, but the formula is too long. So I just use the derivation. So ax, ay, az. This will be the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And for the last part, it should be the components of f. X component is 3x. This is the x component. F of x, this is the y component. F of y, and this is the z component, f of z. So the x component is 3x z squared. The y component is negative yz, and the z component is x plus 2 times z. And we do this method again. Just copy the first two column here, Then I'll just multiply the one going down will be positive. So these are positive. The one going up will be negative. So this will be negative. Minus, minus, minus. Then, you can now multiply them. So this will be equal to ax. So for the positives, ax, partial derivative of x, partial derivative with respect to y, or we can just directly solve that. Partial derivative of x plus 2z with respect to y, that's just equal to 0. Next, plus ay, partial derivative of this one, 3x, partial derivative of 3x z squared with respect to z. 3x is just a constant. Then you multiply it with 2. So 2 times 3x is just 6x. 6x times z. Then you multiply the direction here, ay. And for this, partial derivative with respect to x, negative y times z. That's again without x in the term. So that will be equal to 0. Plus 0. Then minus. So for the blue lines, here, partial derivative with respect to y of 3x z squared. That is again 0. Then for the second one, partial derivative of negative yz with respect to z is just minus y in the x direction. Then lastly, partial derivative of x, x plus 2z, and that is just equal to 1. And the derivative of 2z is 0. So 1, so plus ay, 1 times ay. Then simplify this. So this will be equal to, for the x component, we have negative, negative. So positive ax. For the y component, we have plus 6xz, 6xz, and we have minus 1 here, minus 1 for the y. And we don't have z component here. So this is the cross product. Then we take again the cross product of this one because we want to determine the curl of this again. So the crossed product of the cross product of del and f. So repeat the process again. Ax, ay, az. Then we have partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Then the components, y, this is 6xz minus 1, and we have 0. And copy this. Then let's do the multiplication again. So for the one going down, so we have partial derivative of 0, that's just 0. Then this one, partial derivative of z of y with respect, partial derivative of y with respect to z is 0. So plus 0 again. Then lastly, for the az component, partial derivative of 6 as z minus 1 with respect to x. That's just equal to 6z. So plus 6z because x is constant. That is in az direction. Then for the negative, so here we have az, partial derivative of y with respect to y. So that's just 1 times az. And for ax, partial derivative of z, this one is 6x because this is constant. Well, derivative of 1 is 0. So this will be plus 6x in the z direction. And for the y, it's just equal to 0. So plus 0. So this will be equal to, for we don't have ax. Is it a? Is this az? Still az? It should be. This is wrong. This is wrong. This should be ax because this one is az. This is ax. So we have negative 6x ax. Then we don't have ay anymore. Then plus 6z az. We still have 1 az here. So this should be minus az, or just subtract 1. 6z minus 1 az. So this is our curl of the curl. Curl of the curl of f. But you want to determine the actual a vector at point 1, 1, 2 again. So x is equal to 1, y is equal to 1, and z is equal to 2. So the actual vector now of the curl, so curl of the curl of f will now be equal to negative 6 times x, or x is 1, so this will be negative 6ax. Then for the z, we have z equals 2. So 6 times 2 is 12, minus 1 is 11. So plus 11az. So this is now the vector, the curl of f. So this is how we determine the curl of a vector. We determine the divergence of a vector, and we also determine the gradient of a scalar field.